Thank you for coming in this Saturday morning. So let's start today's session. The first speaker is Sakura, and she's going to tell us about F theory. Yep. Please.
Great, thank you very much for the invitation to speak here at this extremely inspiring conference. And thank you for coming so early on Saturday morning. That's definitely not something that you can assume people do. So what I'd like to talk about is F theory, and we've heard sort of already some talk on related aspects, but what I'd like to sort of focus on are global aspects of recent F theory compactifications, and also, being a physicist, sort of going a little bit into the direction of why physicists actually are looking at it, and the mathematicians shouldn't be running out at this moment, but it's sort of something that hopefully you'll be convinced is tied into the interesting mathematical structures that we find in F theory. Okay, and this is work in collaboration with Joe Marsano at UChicago, Natalia Salina at PI, and Matt Dolan and Durham. Okay, so usually I would start this talk motivating this work by these two questions. So is there any realistic particle physics within string theory, and do we learn anything from embedding this into string theory for the low energy physics? Now, this being the string math conference, I certainly cannot motivate my talk with that. So what I'd like to replace that with is, presumably, is there any interesting math in this kind of constructions? And the second question from sort of the whole 1 week of talks, presumably shouldn't be, is there any imprint on the low energy physics, but actually, can I go and categorify it? Now, certainly I'm not going to go into this here, but yeah, there are lots of mathematicians who presumably want to, or perhaps want to think about this. Okay, so F theory has been basically from the start, when Schafer came up with it, of interest to mathematicians. There's a whole lot of people, in particular all of the Penn math group and geometry group, essentially sort of having an interest in the structure of singular elliptical vibrations, in particular Calabi-Yau's, then also in the context of heterotic F theory duality, and then also applications of spectral covers. So this is not anything new that mathematicians have interest in F theory. The motivation from physics is really mostly that we can sort of geometrically engineer supersymmetric gauge theories. And there are two recent developments applying this, which is mainly the sort of landscape studies that Waddy Taylor, Dave Morrison, and students have been pushing. And then this other development, engineering of grand unified theories, which is what I'm going to be talking about. And there's a whole lot of people who have contributed this, starting with this work here by Ron and Martin, and then Wiesek and Rafa, and following lots of other people. Okay, so that's from F theory. Well, F theory constructions of realistic models of particle physics bring up not only these interesting geometric structures like elliptically fibered Calabi-Yau's, but you actually get a bonus of having surprisingly robust and constraining physics that comes out of this. So you take this kind of compactification seriously, you look at what are the mathematical constraints, and then indeed the physics actually turns out to be also interesting. And I think that's sort of a connection that we haven't really seen. We've always gone from the interesting string theory compactifications to interesting math, and here I think we can also go slightly backwards. Okay, so the minimal physics requirements that we need for this kind of development here is we would like to, for example, get supersymmetric extension of the standard model. We would like to have unification, so the 3-to-1 gauge group of the standard model should be embedded into something like SU5 or a higher rank gauge group. And then this is sort of another additional requirement, which is we would like to have U1 symmetries on top of all this, which distinguish, for example, matter from Higgs's. So this is a completely physics motivated.
A discrete symmetry wouldn't do.
It would do too. What I would like to do is focus on gauged U1 symmetries. And the reason is, if once you actually say discrete symmetries, then there is no general story. I think you'll become a much more, specific. I have a Calabi-Yau, I need to check what's coming out. Here, I can make some very general statements about the setup. Okay, so more concretely, we have an SU5 gauge group, then we have matter and Yukawa couplings. So the representations of relevance are the 10 matter representation and the 5-bar matter representation containing all the quarks and leptons and their superpartners. And then in addition, we have these Higgs fields which come in a 5 and a 5-bar. And so from the start, there's nothing really that would tell you the difference between these two things. So there should be something in the theory that distinguishes between those. And then in addition to these representation, we also would like to generate this kind of superpotential coupling. So this is like the down and the up type Yukawa. Okay, so additional requirements, as I already said, we'd like to distinguish between these representations. The main reason for that is if we don't do that, all kinds of terrible things can happen. This is a generic feature of these grand unified theories, namely that if we don't have anything, for example, that tells us these two things apart, then the proton would just sort of disappear and there would be no reason why we're here. So this is definitely something that we should take seriously. And as I said, one possibility is to have additional U1s. And then a second additional requirement is starting from this gauge group, SU5, which is sort of the minimal thing where you can embed the SU3, SU2, U1, there has to be some mechanism to break back to the standard model gauge group. And so this is something that has to be incorporated into this construction too. And we'll see these two things actually will become some specific properties of the geometry, which then feeds back into what class of phenomenological models actually come out of that theory. Okay, so the punchline of the talk, put slightly more into the math framework, is we'll generate dots from local singular geometries. We can encode these in terms of Higgs bundles plus some extra data. These we replace by, or we characterize by some spectral data. And then in addition, we have U1 and also so-called G fluxes that naturally arise in this context. And then we can extend this to global constructions. And what we'll find is that indeed this whole setup, including these two additional requirements, will give us a very constrained setup from the physics. All right. So I'll start with some basics for F theory. Then I'll discuss the so-called local limit, which is essentially going to a Higgs bundle description and spectral covers. In that context also what G fluxes are and U1s. And then I'll lift this to global structures and also discuss sort of some geometries that are relevant here. And then, you know, indeed being a physicist, I will actually, so this is sort of the retaliation for the motifs and for the, all the categories. This is where I will can't restrain myself to show a little bit of exciting stuff that comes out of that. All right. So F theory basics, just as a recap, F theory we think of as type 2b vacua, where the axial dilaton tau is allowed to vary. Rafa sort of proposed to geometrize this consistent with the SL2Z duality, S-duality group. And so if you want to look at 4D vacua of that, we need to consider so-called compactifications of F theory on now elliptically fibered Calabi-Yaos, where this elliptic fiber precisely is characterized by tau. So the usual story in string theory is we get the gauge degrees of freedom from branes. In this case, they'll be wrapping some divisors in the base manifold B3. Matter will come from intersections of these branes, chiral matter from gauge fluxes, and Yukawa couplings from intersections of such matter curves. Now this is all nice and fine, but in F theory, sort of the really cool thing is that we can geometrize everything, and sort of all of these structures will be part of this geometry Y4. So singular gauge degrees of freedom arise in F theory from singular fibers in the elliptic fibration. So in particular, these will be of ADE type and will be happening over some divisor S inside the base. And so one other way to think of this is really wrap 7 branes on these cycles, whose low energy degrees of freedom characterize one of these ADE type gauge groups. So geometrically, we can realize this we always assume we have some bias stress form for this Calabi-Yau fourfold. So this is the form where F and G are sections of these bundles here. And then the gauge degrees of freedom, as I said, are localized on the singular loci of the vibration. So those are precisely some components of the discriminant locus delta equals to 0. So what I'll do for the rest of this talk is really specialize to this SU5 case, but that I think is just, motivated from the whole physics point of view. So what I'd like to have is, say, characterized by some coordinate z equals to 0 over the surface S. There should be some SU5 singularity, so delta has the form of z to the 5 times some other part of the discriminant. So one extremely useful thing is once you have a specific singularity over S, you can put the Weierstrass form in the so-called Tate form, where it takes this form here, where these coefficients are sections of these bundles, combinations of the canonical bundle of the base and S, or the normal bundle of S gut inside the base. And this automatically characterizes this SU5 singularity. Now, so far this here is just now the gauge degrees of freedom, and the matter, this is sort of this generic picture intersecting branes, localizing along these intersections are the matter curves, and in this geometric picture they will come from these singularities enhancing over a further codimension, now 2 sublocus in the base. So matter comes from now codimension 2 singularity enhancements. For example, the SU5 will then enhance to either an SU6 or an SO10 gauge group locally, and so then can generate one of these matter multiplets that I was talking about earlier. So this is just an example. Maybe I don't want to go through that in detail. Chiral matter, which is of course the thing that's relevant for these models, is we need in addition switch on a gauge bundle on these matter curves. So if we have some gauge group G sigma that's broken to H times U1, we can introduce a line bundle over that, and then the 0 modes for some representation of H with some U1 charge alpha accounted by this indexing. Okay, and then finally, Yukawa couplings are just intersections of various matter curves. And again, this is now codimension 3 enhancement of the singularity in the geometry, which can happen now to some group GP, which is either SO12, E6, or SU7. Okay, so this was the rough picture. This can all be sort of also seen directly from this Tate form for SU5. So here in codimension 1, we have these SU5 gauge fields. In codimension 2, I said there are the matter curves, so matter is localized there. And indeed, if I put this combination of the sections to 0, that's now codimension 2 locus. That's precisely where there is a local SU6 enhancement of the singularity, or alternatively, z equals a5 equals to 0 gives an SO10. And then if I go further to codimension 3, Yukawa couplings, I was saying, come from intersections of matter curves, or now setting these sections to 0. Okay, so this is now the picture. We have the gauge, degrees of freedom, the matter in codimension 2, and in codimension 3, the Yukawas. And then, of course, we can go further, and in fact, this form, this Tate form for SU5, really just is, you can interpret as setting all these to 0 except for A0 is just an E8 singularity, which you then have unfolded to get this SU5 form. So close to z equals to 0, this Tate takes the form of an E8 singularity that's unfolded to A4. Okay, so that's sort of... You do have A6 too. So there's also an arrow down. But that's not useful. We don't no, it's not on the next slide. It's just, it's not used for anything at the moment, and so that's why I didn't discuss it. But indeed, it just has all these, all these loci are incorporated here. Okay, so we have this picture here. This is always close to the divisor in the base, e equals to 0. So we can now ask, well, is there some effective description of the theory in the limit when we go closer to this brain, and
Sorry,
indeed.
wrong question. If I understood wrong question, is there an A6 locus, or is...
There is, yeah. So there's some
So
combination.
is there physics happening there?
Maybe
Yeah.
rephrase it. Can you do this with intersecting brains, where you can?
No, you can't. So this point you can't do with intersecting.
No, but is it important for your physics, for your phenomenology?
What?
No, she's
To
not
have
gonna
the.
use it for-
Yeah, that's.
So
No,
okay.
I mean, can you tell
All
a
right.
order story with intersecting brains and?
No, you cannot, right? Because how will you get the E6 point?
Yeah, you cannot, but then you start with SU5. So I mean.
Okay, so in any way, I think in intersecting brains, you will not automatically generate the top Yukawa, right? So this is sort of one of the crucial points that
So
you need these exceptional things. I didn't emphasize this so much, but 2B doesn't really give you this coupling here, right? Of course, when you go to heterotic, you can, but then you don't have this kind of thing, which I'll get to now, this local limit, where you essentially replace everything by structures in the gauge theory that lives on the 7 brain. So this is sort of the cartoon of what we have. We have these brains wrapping some cycles. And now, what I was just showing you here is the state form really just tells us there's locally a description in terms of this E8 singularity unfolded to SU5. Now, from the point of view of the 7 brain theory, it really means we can think of this as an effective E8 gauge theory that's been Higgs down to an SU5 by adjoint Bethes. And so one way to think of these sections B, etc., which are the restrictions of the coefficients A in the Tate form, which were global sections over B. So let me just go back, just to recap. So the AMs are sections over all the base, and then I can restrict these just to the SU5, where the SU5 is realized for this divisor as gut. Then these BMs really can be thought of characterizing the Higgs field that breaks this E8 down to an SU5. So these take some form. BM is like trace, Higgs field to the M, B0. Okay, so this is the so-called local limit, which in physics terms is just taking the effective field theory limit in the vicinity of the 7 brain, which is an 8D n equals 1 gauge theory. And now the question is, how do we map this data of the gauge theory to geometric data of this now local K3 or ALE or whatever you want to call it, vibration? So one nice sort of thing to maybe comment here is, if we sort of write on a basis of the 1-1 forms in this vibration and then the dual 2 cycles CI, then we can sort of expand the fluctuations of the omega 4-0 form in terms of some fields phi I, which are the Higgs fields, wedge omega, and the gauge fields of the gauge theory arise from fluctuations of the 3-form field, which is the additional structure that we have in addition to the geometry, right? So in these compactifications, there's always the geometry plus some additional flux, which is the 3-form flux with the 4-form, 3-form potential with the 4-form flux. So what we'd like to do now is characterize this local geometry and also this G4 flux. Okay, so the first point is the description in terms of these Higgs bundles. So we heard already a talk this week by Martin on these, so I'll be quick here. The Higgs field that breaks CA to SU5, we can characterize in terms of its just spectral data. So we just look at sort of essentially the eigenvalues of it, and that here, this combination determined S minus phi, we can now write in terms of the so-called spectral divisor, which is just a combination of these sections that appeared in this local geometry. And so I already said these BMs are just trace phi to the M B0. So the geometric data specify Higgs bundle spectral data in this sense. So if we denote the lambda I, the eigenvalues of phi, then indeed we can just write this in terms of the product of S plus lambda I equals to 0. And then these guys, these lambda I's, are precisely what break the E8 down to an SU5 times the commutant SU5, and then the weights lambda I are precisely the weights of the SU5 representation. Yeah?
Sorry, which representation phi is
It's an adjoint. It's just so if you so then right. But I'm only choosing it so that it breaks it not fully to a U1 to the 8, but just to an SU5 remnant times the commutant, which is another SU5, or more correctly, this generical will actually break to a U1 to the 4th gauge group. So lambda I is precisely the eigenvalues of this adjoint Higgs field when it breaks it to this, specific way that it just keeps one SU5 and from the E8 down to one SU5.
I'm also confused by this diagram.
Okay, so this is just the E8 Dinkin diagram. These lambda i's you can also think of as combinations of the roots of the SU5 perp.
Yeah, but alpha 4 and alpha 5 don't commute.
Sorry? Alpha 4 and alpha 5 don't commute.
Wait.
No, I'm breaking it.
Oh, sorry. Yeah, but I'm confused.
I can choose whatever so you have the E8, you break it to an SU5 dot. And then the remnant will be generic U1 to the 4. Now I can just label, if you want, the corresponding, so in fact, you have, this here would label U1 to the 5 with one trace condition, right? So these just label the weights of that, if you wish.
I thought the commutant SU5 perp is generated by alpha minus theta, alpha 1, alpha 2, alpha 3, not alpha 4, 1 to alpha 4.
No, it's definitely, it has to sit inside the E8, right? So the combination that you get for the weights lambda 1 to lambda 5 with the additional condition that the sum of the lambdas vanishes precisely generates to the SU5 perp, right? Of course, there's one condition which you just said. Here you would have U1 to the 5, and then you just take the additional condition, right? Okay, so this is just the breaking of this E8 down to the SU5 dot. And now, as I was just saying, these lambda i's are just the weights of the phi of the SU5 perp, and the 10 would be labeled by lambda I plus lambda j. And so in this context, really, we can see that the 10 and the 5 bar of the E8 are just labeled by the loci lambda I equals to 0. So this is here, right? And then the 5 bar here is labeled by lambda I plus lambda j is equal to 0. So in this way, one can sort of heuristically understand how the geometry maps to these gauge theory data. Okay, there's one more subtlety though. So this was would just tell you, okay, we'll get from that, independent 10s and independent 5 bars, all labeled, by some weights lambda i's. The story, because we are actually looking at some vibration of these lambda i's over some base, actually is slightly more complicated. Namely, the geometry is specified by these BMs, which we said were really the, were really given in terms of trace phi to the MB0. So these BMs are not just linearly dependent on the lambda I, and so what we'll get is some relation between these and these weights lambda I, which indeed, once we translate it back, means that there's a monodromy group acting on these weights, which is a subgroup of the Y group of the SU5 perp, and will generically identify these. So geometrically, what's happening is these lambda i's, we can think of the volumes of these cycles omega I that I introduced, and they'll be identified under the action of a monodromy. Gauge theoretically, what this means is that the U1s associated to these lambdas get identified, and so generically, there won't be any additional U1 symmetries left. Okay, so one useful way to describe this, as I said, is in terms of the spectral cover. And so if we now have some group G, which acts on there, right, so G is a monodromy group, then the spectral cover can split up into orbits of this monodromy group. So for example, in this case, there'll be just one orbit. There won't be any additional U1 symmetry. In this case, there'll be 3 orbits. And so modulo the trace condition, there'll be 2 additional U1 symmetries. So if these lambda i's transform in a reducible representation of the monodromy group, then C factors into and components, and then we have additional U1 symmetries in this problem. Okay, so far what we did is we had a local geometry near the SU5 singularity. The geometry is encoded in the spectral data of the Higgs bundle, which breaks this EA down to the SU5. Something that I haven't discussed is in the spectral cover we can also describe all the matter curves and the Yukawas. And one important thing is there'll be monodromies, which then tell us, once we know specify these, how many additional U1 symmetries we can get from this breaking of EA to SU5. So the only additional thing that we need to now do is actually discuss the G-flux. And remember, this was sort of important to get these chiral representations. So the G-flux is, as I said, we can write this local sort of in terms of these 1 forms, omega I, and expand these out in terms of F wedge omega. And so there are additional conditions that the G-flux have to satisfy. One is the supersymmetry condition, so G wedge J is equal to 0, and then also flux quantization G plus half C2 of the Calabi-Yau fourfold has to be in H4. So what is the relation to the spectral cover? These omega i's are 1 forms dual to these cycles lambda I that I introduced, and so in particular there'll be monodromies acting also on these. So there's a very natural way you can then sort of discuss these fluxes in terms of these factored spectral covers. Okay, so how to describe now these G fluxes in terms of spectral data, and this sort of what I'll call spectral fluxes. So these 1 forms in the spectral cover, or dually the divisors in C, can be embedded back into Y4, and these will then be just interpreted as the dual 2 forms will be interpreted in terms of G. So the spectral flux is really a line bundle over the spectral cover, or 1 form gamma inside the spectral cover C. And these 2 constraints, supersymmetry and the flux quantization, translate into conditions on this form gamma. And if we have now, for example, a factored spectral cover, C equals, for example, an M-sheeted cover times an N-sheeted cover, there's a very direct way to actually construct fluxes that satisfy both of these conditions, where gamma is just some class inside S gut. Right, so you just take this combination, pulling this class back to the component Cm, and then pulling this back to the component Cn, and this will be a traceless combination. Okay, so this was sort of the local discussion. We had the Higgs bundle, we have a description of the spectral fluxes. The question is now, how do we lift this to global Calabi-Yau fourfolds where we don't take this local limit? You might ask, okay, it seems like the physics is fully captured in terms of this local data. Well, it's not quite so. Global structures of the geometry will enter, for example, tadpole cancellation conditions. Global fluxes are important for example, studies of the superpotential non-perturbative contributions. So there's definitely something that has to be understood here. There are 3 parts that come to mind that one has to understand. One is construction of the resolution of the fourfold, and in particular calculation of chi, of the Euler characteristic, which enters into these physical constraints. And then global fluxes, as I said, will be important in this context of instantons, and then finally construction of the base manifold B3. So in this case, there'll be some additional constraints that will actually don't allow any base manifold, but actually, because there is sort of a physics condition from the gut breaking that actually will tell you that only a certain restricted class of base manifolds is allowed. Okay, so I won't have anything to say about this part here. I'll discuss these 2 points below. So the global G fluxes is something I've been discussing now in the context of these instantons. It's something that's coming out soon. So for the global fluxes, what will play the role of this spectral divisor C? And if we go back to this Tate form Y4, remember, so this is the Tate form Y4, where these are sections over the base B. we can define something that we call the Tate divisor, which is just the same, this part here set to 0. Now, this object will reduce in the vicinity of the gut cycle F gut precisely to the spectral divisor C. And if we now sort of assume we have a local spectral cover, the factors sort of generate a U1, we lift this to the global spectral divisor C Tate that also factors, then again, as before, we can write down easily such G fluxes, which are now just again pullbacks into the M factor and the N factor of this factor Tate divisor minus some component that we require for the yeah.
Are you saying is Tate divisor something that always exists, or is that in a subset or class of models?
No, this always. So whenever you have a Tate, you're starting with a Tate form, which is if we start with an A4 singularity, you can always put it in this form, and then this is just essentially what this Tate divisor is.
You're saying that the spectral surface is always the intersection with the divisor coming to the global focal?
No. What I'm saying is this object here, when I restrict it, take a specific limit. In fact, it's not just a restriction, it's slightly more subtle. You need to take a specific limit so that you're scaling to precisely what we call C, the spectral cover, in the local, in the Higgs bundle picture. Then this object here, right, has that property. That's all I'm saying. I'm not saying that C is given in terms of an intersection of this guy with something else. Was that your question, or? No, you asked the question. Well, he's counting down, but it's like this shining bright light there. But so this is another way to motivate this is also if you look at heterotic F-theory duality and you take the Higgs bundle description, you compactify in terms of this dp9 vibration, right, that you also get from the stable degeneration of heterotic, then this object seems to also be the correct thing to think about. So this is really, you could think of it as the 5-sheeted cover that you get from these lines in the dp9 that are, yeah, precisely. But this is sort of conjecture. It works in that duality, heterotic F-theory. It also, gives the right local limit in that sense. I was saying that you need to take a limit to get to C, but of course no one has proven this. So I think this is something that is presumably conjectural in the sense that we've tested it in 2 different settings, in particular in this setting, which I think is more is sort of an important way to understand this, where you can actually resolve these P1s, understand the resolved singularity at least in terms of this dp9 vibration, and then this is just the union of these 5 lines. Okay, anyway, so when this factors, which is of course then in the local limit saying that there is a U1 symmetry left, then again we can construct the G flux, which is really then the flux corresponding to the U1 that comes from this factorization. This F flux here is a flux that's really the gauge flux associated to that U1. Okay, so this is the global G flux story, and then this whole thing can then be fed into understanding the instanton, D3 instanton contributions, etc. Okay, and so let me just quickly say something about the geometry for these base manifolds. So there's one constraint that I didn't discuss yet, which I mentioned at the beginning, which is the gut breaking. So we start with an SU5. Of course, we don't want the SU5. We want actually the standard model gauge group. So we need to somehow lift these. Once we take the adjoint, break it down to the adjoint of these 3 groups. There are some exotic stuff which we have to lift, and that's done in terms of, in the F-theory context, switching on flux in the U1 direction, that's the so-called hypercharged direction, such that it keeps all the matter multiplets intact so SU5 respecting, but it lifts both the Higgses as well as the zero modes of this here. So these are it restricts correctly to the Higgs, such that it lifts the triplets and keeps the doublets. So this is the physics input. Another input is that we would like to have this to be a massless U1 for obvious phenomenological reasons. So there's some topological condition that has to be imposed so that there's no massing of this U1 gauge boson. And so the condition that's now imposed on this base is there has to be Fy, which has to be dual inside the gut surface to a 2-cycle, and that has to be homologically trivial inside the full base manifold B. So there has to be some, say if E1 minus E2 is this hypercharged flux, and the dual to this hypercharged flux, there has to be some 3-chain that bounds these inside the base. So for example, very generically, S is some del Pezzo surface, F is E1 minus E2, we need some 3-chain which has this boundary here. Okay, so this is now one example how one can construct this. Basically, just starting from P3 with some nodal curve, which locally looks like two lines intersecting, and then blowing up this along this curve here to get this kind of picture. This geometry has a singularity, a conifold singularity, which locally is described in this way, and then this point can then be further blown up, and the exceptional divisor of that blow up is then the gut surface, where automatically these two P1s are homologous. So this is just the kind of P1s that one can use for this hypercharged flux. And then swapping this curve here, one can then get this kind of picture, which is now here as gut is actually del Pezzo, so a higher del Pezzo source, so dp2, and then there are some other divisors which can be really explicitly constructed in this context. One interesting thing is that this, so if you ask a mathematician, so if you have some elliptic vibration, Calabi-Yau fourfold, what do you think the base manifold should be? The first kind of class one would look at is Fanos. This guy turns actually out to be not Fano, but almost Fano, so there's some curve where the anticanonical bundle actually can vanish. So I think one interesting question is to ask, so what kind of base manifolds are actually relevant in this context of these singular Calabi-Yau fourfolds with this additional triviality of this hypercharged flux class. Okay, so this is now 5 minutes. So I will 5 minutes, 7 minutes, fantastic. So I will, for these last minutes, just go through some, I think, interesting physics results, so the mathematicians can now switch off. And so what I was saying in the whole talk is most of the physics is described in terms of factored spectral covers, which realize additional gauge symmetries, U1 symmetries, as well as imposing this gut breaking with hypercharged flux. So what we can show very generally, also from the point of view of the spectral cover, is when you have these two ingredients, you have additional U1 symmetries and you have gut breaking, then the U1 charges always have to satisfy this following relation. So this is just a sum over all the 10 matter curve. Charge times the restriction of the hypercharged flux onto the matter curve has to equal the same sum now of the 5-bar matter curves. Now, if we don't want to have any phenomenological disasters, then this implies that there's always some non-gut exotic stuff in the spectrum. So what you get is you have U1s, which you want for, as I said, photon decay issues. You have gut breaking by hypercharged flux, and this will imply always you will not just get the MSSM, but you will always get some additional multiplets.
Assumption on the charge is
Sorry?
That assumption on the charge.
Well, yeah, this is the assumption of the charges. And the assumption of the charges of this here, that I don't want, this is something I did before you came, which is that the Higgs and the matter has to be separated. Anyway, so we can lift this to global models too, and then, in fact, but really the interesting stuff happens already at this local limit. In fact, this already cuts severely into the parameter space of the models that can be realized. And then lifting it further cuts into this. Essentially comes from the fact that this factored cover, when we lift it, not all the classes actually can be trivial because of this triviality of the hypercharged flux. Anyway, so the punchline is global constraints impose restrictions and are actually not, just for theoretical interest, but actually give us some very small class of models that can be consistent with these kinds of compactifications. And all of this wouldn't actually be visible in just a simple brain picture. All right, so I said this condition here implies that there is always some non-God exotic stuff in these models. We can parameterize this in terms of the decomposition of the 10 and the 5 bar into the SU3 to 1 groups and label these by these degeneracies M and K L. And essentially these are just flux numbers on matter curves. And then we get from all these F-theory models just 4 classes of models which have very simple characterizations in terms of these integers. And then once we actually lift this to global models, then it cuts down actually to essentially only one class of these. Okay, so that's kind of surprising. So we started with something that looked extremely flexible. We had these Calabi-Yau fourfolds, took a local limit. It seems like you can realize an SU5 model, have an additional U1 symmetry, but then all of a sudden there's really only a very limited class of models. So for a physicist, this is sort of the point where you say, hey, this is exciting. Maybe these things are actually something interesting and they have some phenomenology that's worthwhile studying. And certainly models with these kinds of additional multiplets have not been studied by physicists because why would they? Okay, so this is hitting the model with a stick like Paul Seidel said yesterday. I'm not hitting the category with some K theory, but this is really just feeding in these models into the computer and seeing what the spectra of these are. So this side is one example spectrum of a model which comes out of F-theory, and this is sort of an analogous model that a phenomenologist would actually look at. So this is like a minimal model here. And the main difference really from a physics point of view is how these gauginos are looking like. In fact, so one question is, this looks reasonably similar, some different spacings, but can we actually distinguish these two things, for example, at a collider? This is a natural.
So you get different gaugino mass ratios?
Yeah, so that's right. So basically, these guys here, these additional multiplets, feed directly into shifts of delta beta I, which enters into the gaugino masses.
I see.
Right.
So what kind of ratios do you get?
Yeah.
This is very interesting.
Okay, cool. Like we've taken a decoupling limit, and so this is if you just look at this model and this model, this is just sort of a model which has a 10-10 bar, just a standard minimal gauge mediation model. This is a model from F-theory. They have similar features. There's one way you could distinguish these is, for example, with RG invariance. However, that's sort of a very theoretical way you can do that. That's not of any interest. So actual phenomenologists would use a different method and look at, for example, this channel where the superpartners of the these quarks decay all the way up to neutralinos and some leptons and quarks. And then they define some kinetic edges, which is something really you can then try to look for in your data. And there's one kinetic edge, which is really different. That's essentially measuring the difference of the second neutralino and the first neutralino. That's sort of really saying these gauginos, right, where you usually have a fixed ratio in the universal models. In the F-theory models, you get something non-universal, and that's what you see here. And that's really something that you could, if there is a difference, really try to disentangle and distinguish against the minimal model versus the F0 model. Okay, so that was the interlude. So let me just conclude with some immediate questions. Yeah, so it's 0 minutes, time's up. But let me just maybe quickly sort of summarize what I think maybe are interesting directions. So in a punchline, this geometric engineering of guts with matter, Yukawa couplings from singular elliptic fibrate Calabi-Yau's with G-fluxes. There are some directions in math that I think are interesting. So one new input is this kind of higher codimension singularities. And understand Dave Morrison and Waddy Taylor are looking at least these codimension 2 singularities, how you properly resolve these. Then just studying the singular fourfolds and finding the full resolution, computing the Euler characteristic, that's certainly something interesting. And as I understand, there's some work in progress by Yao and his poster who spoke about it. Then one point that I already pointed out is what is the structure of the base manifolds. There's sort of work on elliptic K3s and Calabi-Yau's. Can that be generalized to Calabi-Yau fourfolds? What is the class of these base manifolds that are relevant here? And then in the physics direction, there's really sort of one immediate application of these global G-fluxes, as I said, studying of the DS3 and Santon contributions, and there's also some work here on heterotic F0 duality in that context. All right, so let me thank you for your attention.
So these gauge mass ratios, do you get the fixed characteristic patterns, or is this something that you can sort of
No, this is fixed.
Okay.
And it's fixed. So this here, you can think of these integers here really as characterizing the London isology, so how much you deviate from standard in 1 and 2 and 3. And
so what do you call standard in that notation?
Where you have essentially n and L equal to 0.
Oh, okay.
Right, that's when you have full 10 or 5 bar multiplets. Right? And so now when you switch on, for example, this model, right, n and L, then you get a very specific pattern of the zero mass ratios which differs from standard. And that can then be
so standard was like 1, 2, 6 or whatever.
And then you can feed this back into here and really say how
right. I mean, ultimately we won't have something quite so obscure a combination as that. Well, ultimately we'll actually see, 3 genomes and measure them.
Right, this is really about the distinction. If you, for example, had a model, so you see 3 neutral, like the lowest 2 neutralinos, right? You see them here in the spectrum, then you ask, okay, can I distinguish that model from minimal deconvolution?
Right.
In that instance, right? And indeed, there would be a difference from this F0 and F0 students.
More questions? If not, let's thank her again.